Thanks everyone for coming. I'm happy to introduce Professor Ulrike Hahn. She's a professor at the Department of Psychological Science at Birkbeck College, University of London, where she also serves as director of the Center of Cognition, Computation, and Modeling. Her research interests are categorization, similarity, language acquisition, but first and foremost, questions of human rationality. Her research examines human judgment, decision-making, and the rationality of everyday argument. She's presently particularly interested in the role of perceived source reliability of our beliefs, including our beliefs as parts of a larger communicative social networks and how to build social networks like the talk says. Better networks. So Ulrike is a valued collaborator of the lab and member of the coordinating team of Cyber, right, initiative? Cyber initiative, yeah. And today, yeah, she'll be talking about this very exciting topic. So thank you, Ulrike, for joining us.
Okay, thanks for the introduction. Thanks for the invite. So without further ado, I guess the longer you think about human cognition or humans generally, the more you realize that you can't really understand anything about them without thinking about social influence. So most of what we believe to know, we know via the testimony of others. And we've also learned in the last decade or so that one of the single best predictors of your behavior is just knowing who you know. And that has sort of just increasingly come to the fore, not just sort of my own knowledge, but interests, but the sort of field cognitive science as a whole. A lot of the work in this area has been very sort of descriptive and in trying to understand the sort of dynamics of behavior, of how influence spreads, how opinions spread, behavior spread. I'm really interested in questions of when and how groups are good or bad, or when social influence is good or bad. And we have things there, right? Like, so we've all heard of wisdom of crowds, like that's good about crowds, but we've also heard about group thinking, herding, and polarization. That's also about groups, but that's bad. What I'm trying to understand is when and where is group influence good and why? And I've been specifically interested in the accuracy of our beliefs. Like I've said, if you look, for example, at the kind of massive literature on social networks and opinion dynamics in the last 15 years, the majority of it isn't about this question. It certainly wasn't when I started thinking about this 10 years ago. It isn't even now. And you can just see this from the simple fact that to kind of examine how something about a network might influence the accuracy of your beliefs, you need a simulation context in which there's a ground truth that you can compare to. Right. So in recent years, there's been a little bit of an influx of this because people have become very interested in studying misinformation. And we could get back to that in the questions. But even there, a lot of the simulations just treat misinformation as an arbitrary unit of information that gets propagated through a network. So you're not really looking at anything other than you would say to model disease or something. And so what you're particularly not learning about is what networks do by virtue of being networks, even in contexts where we're all trying to do the best we can. So I'm going to be talking exclusively about contexts where there are just good faith actors. They're trying to have accurate beliefs. And what does group influence do in that context? Now, there is a little literature. This was a sort of hobby horse in psychology, in social psychology in the 60s and 70s. And I wanted to use that as a point of departure because I think there is an important methodological lesson there that sort of shapes how I think about studying these things and shapes the nature and content of the talk. So what people were interested in that literature in the 60s and 70s was they got groups together and these groups deliberated or not. And they did tasks like estimating the number of jelly beans in a jar. And people were then interested in how accurate the group estimate was and how accurate was relative to the best people in the group and the average people in the group and whether deliberation helped or hurt or whatever. And people first got super excited about this. And then the results all got really kind of messy. And that's the sort of point where researchers then sort of up sticks, they're bored with the area and move on. And the problem was really kind of reconciling these seemingly conflicting results. And Robin Hogarth wrote, I think, a very important paper in the late 1970s that pointed out the need for sort of formal tools in this context to really understand these seemingly conflicting results, because these formal tools, and I'll give you examples in a moment, highlight what are sort of opposing forces that are in play in these domains. So it just so happens that I recently wrote a paper last year in Topics that are about the range of formal tools that we have for studying these kinds of questions about the beliefs of collectives and people in collectives. So if people are interested in that, I'm just going to pick out a particular framework to sort of structure this talk. But to be completely sure that everyone's on the same page with respect to understanding the questions and the framework, I want to make clear what we're dealing with is contexts where there are a bunch of values in the world, right, that we're trying to estimate. These could be estimates of number of jelly beans in a jar, the weight of an ox. They could be numbers between 0 and 1, or just zeros and ones reflecting true or false or whatever. And then we're going to have people rating or providing estimates of those values. And what we're interested in is somehow measuring the accuracy of those ratings. So we're going to have some measure to kind of compare the ratings with the true values. And in a group, when we're dealing with a collective, we're going to have multiple of such people. So the obvious thing to do is that we do this individually for each of these people, right? And then to kind of characterize how good they are as individuals, we just take the average of those. And that's our measure of average individual competence. But the other thing that we can do when we have a group like this is that we can average all those ratings. We can derive a mean of those ratings, and we can relate that mean to the target values. That's sort of our measure of collective competence. That's the wisdom of crowd, is the idea that we're expecting that collective competence to be higher than this average individual competence. So here's the formal framework that I want to set this out in. It's very simple. It's called the diversity prediction theorem. You've probably heard of it. And it's very general in that it applies to just a set of estimates and a true value. These could be estimates of any kind. What it assumes is that you're going to measure collective error, i.e. collective competence, in a particular way, namely as the squared deviation between that mean judgment of the group and the true value. And then you're also going to measure the diversity of this group as the variance of the individual estimates around that mean. And then it's the case by mathematical necessity, and if you stare at the equation long enough, you can see why that is, that basically the average individual error is just going to be the collective error plus that variance, the group diversity. And this is already the theorem, and that doesn't look very exciting, but it becomes more interesting if we just rearrange the terms by subtracting group diversity on both sides. So what we then end up with is this, that collective error equals the average individual error minus the group diversity. So that already tells us something profound about wisdom of the crowd, because it shows us that the collective error can't be worse than the average individual error, right? Because at worst, there is zero diversity in the same, they're just the same. But the moment there's any variance in the individual estimates, we're subtracting that diversity there. So the collective error is going to be lower, which is just to say that diversity in the group reduces collective error. And that maybe even more surprisingly, diversity measured in this way and individual error are equally important in bringing about collective competence, right? This equation doesn't say collective error is average individual error minus 1/2 the group diversity or something. It's just minus group diversity. So that's the framework. Now, if we think about that and apply that to the way people communicate across social networks, right? I talked to Gordon. Gordon also knows Steve. Steve knows Dawn. I also know Dawn, right? We're always talking to people who are also talking to other people. And that gives rise to a sort of network structure. And the structure of that network is going to affect, to determine the paths of communication. It's going to affect the dependence or the degree of correlation between people. So it's going to affect the sort of variance or diversity. So we would expect, in light of thinking about something like the diversity prediction theorem, that we might be able to see systematic effects of network structure, even if the people involved stay completely the same, on the accuracy of our beliefs. And that's the question that I've been concerning myself with for quite a while now. So there are indeed now a number of behavioral studies in the literature that show that there are systematic effects of network structure on accuracy. I'm going to describe briefly just one of these studies. To the best of my knowledge, it's the first one. It's a study that we conducted when I was in Sweden in 2013, 2014. And what happened here is that we got people into the lab and you answered a bunch of exciting questions about Sweden. So estimates such as the proportion of Swedes under the age of 21 that drink alcohol and so on. And we had the answers from the sort of Swedish equivalent of the Office of National Statistics. You entered your answer on the computer and you were connected to other people in this room, though you didn't know who you were connected to. And you then, after giving your answer, saw the answers of those people. You could then revise your own estimate in light of what you saw, and that went on for multiple rounds. And then you got a new question and the whole thing repeated. So unbeknownst to you, we manipulated the structure, the connectivity by which you were connected to other people. And in particular, we put people either in a condition where you were connected to everybody else in the group, so there's a complete graph, or there was a small world network, which is a practically important, prevalent network structure that's characterized by short path lengths and high degrees of clustering. And this is what we found. So first, these are the average individual competence. This is now called validity because actually good numbers are high here and not errors. And what we see is that basically people got better after revising multiple rounds of seeing other people's estimates of the same question and revising their own answer. On average, and they did so for both the complete network and the small world network. But this is what happens with respect to the collective competence, that is the wisdom of crowd effect. Now, first of all, we see that there is a wisdom of crowd effect. That's comforting because there should be one, right? In that both of these lines are higher than those lines. But we now also see here a difference between the competence of the small world network and the complete network. So the small world network is actually better than the complete network, even though there's less communication and less information exchange going on. And that, of course, makes sense to you now, given the diversity prediction theorem, because what's varying across these two networks is also the amount of correlation that's forming. That is the dependence and the reduction in diversity that we're seeing. So across rounds, across questions, we see that the average pairwise correlation between two people in this in these networks is higher in the complete network than it is in the small world network. And just to kind of completely hammer home that this is not just a good thing, we thought of the following measure, which we called excess correlation. So what this is about is that any measure of accuracy, right, is a distance measure, like how far am I from the true value? And distances have to follow certain general properties. So the distance that I have from Steve and the distance that Dawn has from Steve also constrain how far Dawn and I can be apart. So if we think of Steve as the sort of true target value, how accurate Dawn and I are, i.e. how close to Steve, also constrains how close we have to be to each other. So what we basically did is that we calculated for a given degree of accuracy that two people had, how close they would have to be to each other, given how close they were to the true target value in correlation terms. And what excess correlation shows you is how much closer they are than that accuracy mandated correlation. So excess correlation basically is a measure of correlation that isn't accuracy enhancing. It's Dawn and I being more correlated than we need to be on the basis of just how close we are to Steve. And it's this excess correlation that is higher in the complete network than in the small world network. So there are other studies kind of to this effect. So topology modifies accuracy in behavioral experiments. It also does so in simulations. So in this paper here that we wrote in 2020, we were using an agent-based model that was first proposed by Eric Olson. You don't really have to know very much about this model at all. For the purposes of this talk, it involves these naive Bayesian agents. They live in this exciting world where there's one claim at issue, and they receive on a given time step information both from the world and potentially from others via communication. Where these agents communicate their beliefs, their present beliefs. In particular, they say a claim is true when a certain threshold degree of belief is exceeded. And what we found in those simulations was, again, this is now a plot of collective error across different types of networks, is first of all, a replication of the behavioral result that I just showed you, and that the collective error now, high bars are bad, are higher for a fully connected complete network than for the small world network, just as in these lab studies. But maybe more interesting, we also found significant differences of network topology, that is how you're connected, structure, even for networks that had the same number of nodes and the same number of connections. And the only thing that changed is how those connections ran. And this includes networks that are completely identical other than for a single link that's been changed. And because we can run zillions of these, any difference you can make out by the naked eye is a significant difference in this context. And it should also not surprise you, in light of the diversity prediction theorem, that the networks that are best for reducing collective error are not necessarily the networks that are the best for reducing individual error, right? So the best network from a collective error perspective is just a chain, but that's not the best network if you're trying to make people individually as accurate as possible. So all of this tells us that the mere structure of our social networks changes the accuracy of our beliefs, even if we're otherwise exactly the same and everybody's doing the best they can. And actually, in the case of the simulations, is as rational as you could possibly be in these contexts. And we have sort of convergent evidence of this from simulations, from behavioral experiments, and we kind of understand what's going on there and why this should happen from mathematical results like the diversity prediction theorem. So why is this interesting? Well, I think one of the reasons it's interesting, and certainly was interesting to me, is that it sort of puts a particular spin on the question of like, what on earth did we think was going to happen when 15 years ago, we started to allow social media tech companies to fundamentally alter the structure of our communication networks, right? We basically have been living as societies in this massive experiment where we let Mark Zuckerberg go out with his project of trying to connect everybody in the world, which is a kind of completely unprecedented sort of change in topology and scale of our social networks. Now, when I first started this a decade ago, if you sort of expressed concern about the role of social networks, people basically sort of told you that you were the kind of person who was also hostile to the introduction of the telegraph and the radio and email and so on, and that these things were just platforms. But of course, they're not just platforms, because what they're doing is altering the topology of our networks. So even if social media had no other properties and did nothing other than massively increase the size or alter our communication networks relative to before, we would have expected some kind of impact on the accuracy of our individual and collective beliefs. But of course, what we've done in actual fact and what we've let them do is something much worse. And you're all aware of this, is because we've basically outsourced now a significant part of our public discourse to this kind of hybrid human AI, because of course, these systems are run on algorithms that nobody really understands properly. And these algorithms are generated and maximized for a quantity that isn't actually the accuracy of our beliefs. And it would be truly miraculous if maximizing advertising revenue turned out to be exactly the same thing as rewiring networks to maximize collective or individual accuracy. But all that raises the question of what would we do if we got to own our own networks, right? And instead of trying to maximize advertising revenue, we now try to set these networks up in such a way that they made us more accurate, gave us better beliefs. Now, there's range of things that you can do and that people are already doing to various extent. An obvious one is you can kind of remove false content, or you can ban actors that systematically promote false content. But these are kind of quite problematic, right? Other than in special circumstances, like we probably all don't really want to live in a world where courts decide about what's true or false, and all of that's sort of a little bit awkward. So we might also want to go down the other route, which is promoting higher accuracy commentators, right? You give them more weight in the network, and that's a nice idea, except in many contexts, we don't already know the truth or falsity of what we're discussing. So in that context, it's not entirely clear what it means to be a higher accuracy commentator. Like, even if you have a track record, you were amazing in physics, you might not be so great in commenting on COVID. And the point about a discussion on COVID, for example, is that we're talking about things that are as yet to happen, and we don't know whether they're true or false. So is there something that we could do in those contexts where we don't yet know a ground truth to promote accuracy? And that's a question that I spent some time thinking about in recent years with my PhD student, Jason Burton. And specifically, we were interested in this question of whether you could figure out ways, even in principle, to dynamically rewire networks while discussions were unfolding in such a way as to promote the accuracy of people's beliefs in those networks, even though you didn't yet know what was true or false. And so we started with a model, and in this model, there are 16 agents, and they're placed in a randomly generated network and seeded with an initial belief. So they get, somewhere between 1 and 10 pieces of evidence, and we vary the evidence quality according to the sensitivity and the specificity, basically the hit rate and the false positive rate of that information. And then we let these simulated agents communicate with one another and update their beliefs over time, exactly like in this Lund lab study that I described to you. Now it's just these simulated agents doing the same thing. And they're updating their beliefs according to an equation which we can just actually take from published behavioral experiments, including our own, of how people behave in those lab contexts. So we kind of know what they do there. And what people do is they sort of take a weighted average between their own beliefs and the beliefs of the group. And we just run beliefs through this over time. And then after 5 time points, we look at the collective average belief of this kind of network and calculate an error. And what we're interested in is whether we can have algorithms that make things better or for worse. And we considered 2 algorithms. First, we have a static network. That's the network, at the top, where the connections just stay the same. And these are sort of beliefs changing over time. This is just a distribution of beliefs between 0 and 1. And on the bottom, we have one of these dynamically rewired networks and how its beliefs are changing over time. And this particular algorithm, the mean extreme algorithm, basically looks at what the mean is of the current beliefs And then it finds those people who have even more extreme beliefs than the mean, so like the sort of caricature of what the group presently believes, and it gives those people more connections, taking some away from other people. So those extreme people will pull everybody toward the mean. And the polarized algorithm basically does the opposite. So here you're taking the people who are furthest away from the mean, giving them some extra connection. So you're pulling everybody away from that mean. And of course, if everybody's right, that sounds crazy. But given what we talked about, the interrelationship with collective accuracy, individual accuracy, and variance, this is going to increase the variance. There might be value in that. And then we ran these simulations, and this is what we found. So the way to read this plot is to think that we've ordered these according to the quality of the initial evidence. So this is more initial accuracy. This is more initial accuracy. So here they are least accurate initially. Here they're most accurate initially. And we look at three different measures: collective error, the average individual error, and the variance, like the quantities of diversity prediction theorem. And what we're showing is change relative to the static network for both the mean extreme algorithm and the polarized algorithm. And what happens there, of course, understandably changes as a result of the initial distribution of beliefs and that accuracy. So here, there's a lot of noise, and you're basically just pushing that noise around. So there's not that much improvement. Here, everybody's already really good at the beginning, so there's little room for improvement. And so the action is somewhere in between there. And in that in-between space, the mean extreme algorithm improves performance, both collectively and individually. And the polarized algorithm does the opposite. So that's kind of nice and interesting, maybe. But what happens if we take this basic idea to an empirical experiment, right? Where we're going to try to do the same thing as like modify accuracy just on the basis of knowledge about where people are in the overall belief distribution without reference to a known ground truth. So we ran an experimental study, and here people had to answer questions like, what's the chance that a particular number of COVID deaths will go above 900 in this time interval. So these were all about future events. So the answer wasn't yet known, and we could only score and resolve this after these events had taken place. And again, like in the Lund study, you give an estimate, you then see other people's answers, you revise your estimate, and so on over multiple rounds. This is what we found. Now expressed in terms of change, but not change relative to the static network, but rather change relative to the initial beliefs of the people in the group. And what we see here is this is the static network condition. These are the polarized networks, and these are the mean extreme networks. And what we see is that if we look at change within a group, right, there's a benefit of the polarized algorithm. There's a detriment to the kind of mean extreme algorithm. We also see kind of huge amounts of variance, right? These are individual groups. The problem with experiments like this is that groups are now your subject. So this study literally costs thousands of pounds, but you don't have very many participants, right? Because your participants are groups. And they have a lot of variability in the initial beliefs, which is why only this within group change measure works. If you just look at group performance without basically controlling for that, you don't kind of find a significant effect, but that's sort of in the nature of the beast. So the more interesting question about this is now this seems like the reverse result from what we had in the simulations. Now it's polarized, that works, mean extreme doesn't. Why is that? So the obvious thing to look at is the initial belief distributions. These are the initial belief distributions, those quadrants, those that I showed you, ordered from least accurate, from most accurate to least accurate. And this is the same for the initial beliefs in the actual experiment, ordered in the same way across topics. And what we see is that basically for none of these topics, none of these belief distributions matter. So if we're going to make progress with this in the real world, we're going to have to kind of learn more about the impact of distributions on the performance of these different algorithms. So the way we then went about this was to basically take a large data set of real world, of experimental tasks with judgments that Abdallah Almatuk has assembled. He's basically compiled 57 estimation tasks that people have run in these collective contexts that are made up of 4,000 individual judgments. And we used that data set to just sample initial beliefs. And then we used the same belief rule, revision rule that's sort of empirically grounded that I've already shown you, to then simulate what would happen in these hypothetical networks, given these individual beliefs. And this is what we found. So the quantity we're graphing here is the skew of those initial distributions. And these are the 57 tasks, a histogram of these 57 tasks, data sets with respect to their skew. And here on the right hand, we've plotted the number of times a particular algorithm, polarized meaning stream or static, this isn't no communication, it's no rewiring, number of times that algorithm was the best in those simulations. And what we see is that the relative performance of these algorithms shifts as a function of that initial skew. And so, of course, this is nice because skew is a property. It's a property of the distribution that you can track. You don't need to know the ground truth about this. So it looks like there's something there that you might be able to hang something on in terms of trying to identify under which conditions a particular type of rewiring algorithm might or might not be beneficial. So all of this, of course, is just proof of concept, right? The whole first part of the talk made a big song and dance about how changing the topology and the scale of our networks changes what happens in those networks. So there's absolutely no way in hell that what we've done with 16 people is going to just magically scale to larger networks. Also means, unfortunately, that really you can only work out exactly what's going to happen with larger networks if you can manipulate larger networks. And that just echoes other sort of movements already afoot, including ones that Steve has been involved in that have been making this point that if you really want to understand what's going on in the real world and avoid some of the pathologies of large-scale online platforms, we need to be able to conduct studies at that scale. So just to wrap, I tried to highlight the interesting theoretical interconnections between collective accuracy, individual accuracy, and interdependence. And I think you need to understand those fundamentally if you want to understand anything in a kind of communication context. As a result of these interdependencies, we can find systematic differences on the accuracy of our beliefs, both individually and collectively, as a function of network structure. And we can potentially harness this, at least in principle, to improve the accuracy of our beliefs. So there seem to be systematic relationships between belief distributions, the skew of those, and the impact of potential rewiring algorithms for boosting accuracy. But to really get somewhere with this on a grand scale, we're going to be able to mess around with this on a grand scale, which means we need to be able to do what tech companies already can do. So with that, I've got to the end. Thanks for your attention. Thanks also to my numerous collaborators on these projects over the years. First and foremost, in the context of this talk, Jason Burton, the rewiring stuff was part of his PhD. He's now a lecturer at Copenhagen Business School, and he's carrying on with this work, or will be carrying on with this work in the context of a Humboldt Fellowship at the MPI in Berlin. So that's me done. Thank you.
Thank you so much, Ulrike. As you suggested, I'll stop the recording now, so we'll move to the discussion part.